discuss about crane stability. So basically, in crane stability, there are two main things that should be considered in designing a stable heavy lifting arrangement. First, it's stable based on the load capacity, and the second is stable in COG. But the COG here is not only talking about the structure, but also all the items from the structure to the crane's equipment, like hook, boom, carrier, uh, mast, crawler, counterweight, and anything else. So with the COG information, we will not only check the stability based on the tilting angle, but also we will estimate what is the ground bearing pressure below the crane. So we will start from a type of cranes. Basically, there are two types of crane. They are mobile crane and static cranes. As its name, mobile crane is type of crane that can move from location to location. Generally, they have a bigger capacity than the static crane. Unlike the mobile crane, static crane can only stay in one place. So basically, it cannot move. It can only can slewing or rotating or changing the radius by boom up or down and moving the hook with its bogie. Now let's see what are cranes which include to mobile crane and static crane. So the first one is a truck mounted crane. This type of crane usually used due to high mobility, for example, in highway, and outriggers can be used if required to stabilize the contact point to the ground. As we know, one of the characteristic of the rubber tire is elastic. So when doing the lifting, the COG of the crane is not always exactly at the center. Sometimes it's offset at certain millimeters, for example. So this offset will impact to the load distribution, and so the load on the tire will be different each other. If the load are not same between the tires, then the deflection of each tire will be different as well. It will be the same situation like we are doing lifting with the crane on an uncompacted soil. So, and trust me, that's not really good, right? So the capacity of this type of crane also not really huge, about 10 to 100 tons. It depends on the type and the manufacturers. But some need to be considered to use this crane is its flexibility. Suitable for light construction, can be used for also for material distribution or transfer from one place to another, as it has a space for cargo at the behind. The next one is crawler crane. We all know this type of crane, yeah. I think everybody familiar with this type of crane. So this type of crane has high stability as its crawler or tracks, giving more contact surface to the ground. It's capable to be operated on a rough area like a soft ground, but we need to do study and decide what treatment does the ground need and what is the requirement, because not some soft ground we need to do some treatment so that the pressure from the crane will be distributed normally to the ground. This type of crane also has a huge capacity. The maximum crane capacity that I've ever used in project is about 3,000 tons, if I'm not mistaken. It was a Lamson crane, if you know about that in McDermott. So and this crane also has a flexibility in boom length selection, but not as flexible as the telescopic boom. However, you still can choose what length of boom you require in your lifting plan and then assemble them separately. Besides all the pros that we already discussed, this type of crane also has a cons. They are limited on mobility and long setup time. And then we continue with the another mobile crane. It's a rough terrain crane. The next one is a rough terrain crane. Uh, this type of crane has more flexibility than the all-terrain crane. So we have two type, the same type as like the rough terrain crane. One is a rough terrain crane itself. The second is all-terrain crane. So first, this time we will discuss about the rough terrain crane. So uh, this type of crane is has more flexibility than the all-terrain crane and capable to be operated in challenging areas. And the size is more compact. This crane also equipped with outrigger. So if it's required, you can use the outriggers to give you more stability in the lifting. Same like the truck mounted crane. The minus is limited in capacity and boom length. The After the rough terrain crane, we also know all-terrain crane. This type of crane offering high mobility and rough terrain capacity. It's like many truck, this crane can travel in the highway. And like a rough terrain crane, this crane also can travel on a rough way. So it's a combine between the truck-mounted crane with the rafter and crane. This crane now offering a large capacity also. Some of them can reach up to 1,000 tons. Advanced suspension and steering system for high flexibility also its advantage. But price could be the problem as it's more expensive than the rough terrain crane. So the conclusion in choosing what cranes do we need, right? So now we go to the conclusion. The truck-mounted crane is the best choice if highway mobility is needed, with medium capacity and ease of use. Crawler crane suitable for heavy projects in rock or muddy terrain, but always do ground bearing pressure study before and do treatment if required. Rough terrain crane is a solution for rocky and uneven terrain that cannot be used in highways. And if you need a flexibility in lifting operation, you can rely on this crane. All-terrain crane is the best, the option, not the best, but another option if you want to combine high mobility and capacity, but a little bit pricey. The next one is another type of mobile crane. I think some of us also familiar with this, the floating crane. This type of crane is a crane that mounted onto a barge or vessel so that you can do the lifting operation on the water. It use water ballasting system as a stability. We will not discuss about this type of crane in this program. We are still developing a detail about this crane, and we will launching it soon in a advanced class. So that's for the mobile crane. Now we go to the static crane here. We continue with the static crane. First is there is a tower crane. A tower crane is a fixed crane used to construct high-rise buildings and large infrastructure projects. Due to its extended design, this crane has a high lifting capacity and can cover a wide working area. High lifting capacity, it it can lift between 10 to 80 tons, depending on the model configuration. Wide range, the horizontal boom allows the crane to reach a radius up until 80 meters, and the adjustable height can reach 100 meters or more with a climbing frame system. And then space efficient, suitable for dense urban areas as it remains fixed in the one location. And then stationary operation, unlike a mobile crane, a tower crane remains fixed throughout the project. Long erection and dismantling process requires additional cranes if required for installation and disassembly. And then because it's very high, then of course it will be sensitive to strong winds. Stability must be considered to withstand adverse weather condition. And then we have laughing tower crane here. Unlike the tower crane, which can move the hook position, this laughing tower crane needs to boom up and boom down to adjust the radius. And then used in urban projects for with a limited space and then more complex and expensive compared to the hammerhead crane. And then we continue with the cranes component. So first is component of crawler crane. In the crawler crane, there is a lattice boom. This is a lattice boom that need to be assembled every time we need to extend or to shorten as required. And also we can attach the flying jeep here if required. Another component is a hook here. This is where we attach the load with a set of rigging. And then the next is the crawler or track here. This is where the contact area between the crane and the ground underneath. The track sizes are different for each crane, depends on the crane manufacturer and type. So make sure you have this information before doing a lifting plan. And then the next one is counterweight here. This component is important to keep our crane COG in balanced position. Some of crane also has a additional counterweight behind, and it's called superlift counterweight. So the superlift will usually at here. That's the additional counterweight, and usually there is additional mast to connect the two lift. Sometimes it's a lifted counterweight. Sometimes it's there is a tire on the wagon here. So yeah, so that that's the purpose is same as the counterweight to keep the crane COG in the balanced position. So that will increase the capacity as well. So yeah, that's the main component from the crawler crane. And the next one is rough terrain crane. This type of crane has a telescopic boom. This. So telescopic boom doesn't need assembly if longer or shortened boom is required. We can simply just push the button and then the boom will be automatically extend or shorten based on our requirement. And another component is outrigger. Outrigger is this. This is the contact area or foundation of the crane to transfer the load to the ground. Some of crane in this type can also stand on its tire during lifting. Uh, This type of crane also equipped with the counterweight at behind to make the purpose is also same with the crawler crane, just to make the COG keep in balanced position. And that's for rough terrain crane. The difference with all terrain crane is that only on the driving mode configuration. Other component are basically same. We continue with the codes and reference that I usually use in my design or in lifting plan. But not limited, you can choose any codes or references that suit your to your project there. So there are three references in here. They are first is DNV OSH 205 about lifting operation. And then IMCA M1X7 also about talking about the lifting operation. And the last one is ASME B30.5 about mobile and locomotive cranes. So that's the codes and reference I usually use, but not limited. You can choose whatever codes or reference that suitable with your current project or your company. Now we will uh so yeah, now we are seeing how the outrigger's load can be changed in mobile cranes. What does make it changing? That's the first question, right? The answer is COG. As we see in this picture that I've taken from Australian standard, if I'm not mistaken, when the load is not attached to the crane, like a like showing in the left column, yeah, here, no load on the hook. The maximum outrigger forces appear at the behind of the boom, which is where the counterweight is located. So when there is no load, the crane COG more affected by the counterweight itself, so that the COG will be at behind the center of the crane. And just for your reference, when I say center of the crane, it means center of the slew ring. So if if we refers to this, then the sorry. So if this is the slew ring, center of the slew ring is the center where the boom will be rotated. So if the center of slew ring here, right, then the counterweight is here, and the hook is here. When it's when there is no load on the hook, then the COG only affected by the counterweight. That's why when we calculated the COG, it will be appear at the uh, behind or at the behind of the center of the slurring. That's why the maximum outrigger forces will be uh on the back of the rear outrigger. So yeah. So we in every calculation we will use the center of the slew ring as our reference point. So yeah, we continue with the load attached to the crane. As we see in the right column here, what's gonna happen if we put the load to the hook and then the COG? will be started to move to the front of the center. Why? Because the moment force that caused by the counterweight is countered by the moment force caused by the load itself. So if we look at if you know seesaw, right? Seesaw. Let's say the counterweight is here. And then when there is no load, the COG will be at the behind of the of the fixity. So it will be here. Let's say here. That's why the this member will be deflected like this. But when we put the load at the front here, it will counter this counterweight load so that the COG will start it to move to the front here. So actually this all only talk about the balance between the front load and the rear load. And then from that we can calculate the COG, and then the COG will distribute to the foundation, which is if it's outrigger, then it will be distributed to the outrigger. If it's a crawler crane, then it will be distributed to the crawler. So I hope all of us has familiar with the COG calculations before we talk about the this crane stability. And it, yeah, I hope. So yeah, as we will see the sample of calculation after this. So as we know, the formula of moment force is a load times distance, right? So that means big or small of moment forces will depend on the load and the distance. Or in this case, we will say it's a radius. Or and then the longer radius we have, it will give a bigger moment to rotate the crane to the front, while the counterweight gives a moment forces to counter it. The next one is the ground bearing pressure under crawler crane. It also will change, depends on the COG location. When there is no load here, when there is no load, the COG will be appear at the behind, because the COG only affected by the counterweight. And when there is a load attached, so when there is no load, the COG, let's say this is the slew bearing center, then the COG will be at the back of the center. But when there is a load, the COG will be started to move to the front of the center. Uh, that's the same reason as previously for the outrigger forces. So we will discuss about this later. So don't worry about this. So it will be detailed explained after in the correct time. So yeah, that's all for the part one. So before we get into crane stability calculation, I will recommend you to understand how to calculate the COG of crane during lifting, because we will not discuss about this in this program. So basically, it is same as a structure's COG calculation. So we only need to know what are the components, what the weight, and where are they located. That's all. So yeah, that's for the part one. Is there any question before we continue to the part two? Any question?
Any question before we start to calculation?
So far, so good. Thank you.
So far, so good. Okay.
Okay. All right. If no question, we will continue with the part 2. Yep, there you go. So, in this part 2, we will discuss about crane stability based on the load capacity. So there are several factors that should be considered to check crane stability based on the load capacity. They are additional loads due to uncertainties in the lifted object's weight and COG. We called it as gross weight. And then the next is crane hook weight. This should be considered if the capacity of the crane in the load chart is gross capacity. Later we will see what is the gross capacity and what is the the net capacity. Next is rigging weight. This also needs to be considered as it will give additional load below the hook. And then we have dynamic load. Dynamic load is a additional load that caused by external environment like wind, cranes movement, wave, hook movement, or anything else that could possibly make the object move horizontally or vertically. But we will not discuss about the dynamic load more detail in this class. We will just simply by using the dynamic factor. And if you're interested to learn about the more about the dynamic, we will open this topic in advanced class. So right now we will just discuss about the basic only. And the last one is additional load due to multi-crane operation. This we call as skew. Same as the dynamic, there's a factor that we should apply if we are working with the multi-cranes arrangement. So in crane capacity, there are two types of capacity that we can see in the load chart. It will depend on the crane's manufacturer. However, it always mentioned in the catalog or in the load chart if the capacity shown in our net or gross. Now, what is the net capacity of crane? It is the crane capacities which you already consider weight of the hook and ribbing or path line, while the gross capacity is crane capacities which haven't considered the hook and ribbing weight. So we need to calculate the hook and ribbing weight and consider it in the load calculation. For example, it's shown in this load chart that I took from LTM 1200. This is a all-terrain type, and I assume the configuration ST or main boom only. If we look at the note number 4, we can see that it is mentioned the hook block and parts are part of the loads. So in the other words, we can say that the crane capacities in the load chart are gross capacities, right? Now, let's see the load chart. I hope all of you are already familiar on how to read the crane load chart or crane table. As we've seen here, there are many tables that showing the crane capacities in several radius. So before you start to have a look at the crane table, make sure you have all the information of the crane that you're gonna use, like the counterweight configuration, radius, boom configuration, and then is there any jib attached to the boom? What is the type of the hook? If the manufacturer gives multiple hook option, and then is a crane allowed to slewing and anything else? For example, for this type of crane, let's say the counterweight exists right now is 72 ton, right here. And in our lifting plan, let's say we need 12-meter radius and 40.3 boom length, and we need to slew the boom. From the crane table, we will get the capacity of this crane is 42.4 here. So this is the radius here. This is radius, and then this is the boom length. And this is the counterweight, 72 ton, and outrigger attached. I mean, it's extended. So yeah, we for the radius 12-meter radius, then we got 42.4 tons capacity. But if slewing the boom is not allowed, possibly we will need a different crane table, because in here it is mentioned that the slewing is allowed on this crane, and but sometimes there is a separate crane table that specific for the stationary boom. So I mean, the boom, it's not allowed to rotating, and it will gives more capacity to the crane if it's not rotating. Okay, so you need to see the correct load chart. If it's allowed to slewing the boom, then we can use this we can use this crane table. But if it's not allowed, then we can choose another crane table, which is bigger, having a bigger capacity than this table. So that depends on what the manufacturer says in the manual. So make sure you are familiar with the cranes manual before you use it. And no need very detailed, but at least you have reason to choose something, right? And this is also the crane table for this table is for counterweight 42 tons, and that's here. And the right one is 32 tons here. So make sure you have the cranes information before you choose the what crane table you want to use. So another example is a crane load chart for a crawler crane LR11350 by Liber. This case, I assume the configuration is SL or main boom only. This crane capacity is also identified as gross capacity, as it is mentioned in the note number 4 here. The weight of hook block and parts are part of load. To read the table, same as the previous crane, we need to get all information about the crane that we are going to use from the boom configuration, counterweight configuration, hook types, jib if any attached, super lift if it's attached, and anything else. And then we can find the capacity based on our requirement. But don't forget to calculate the hook and reefing weight and put that into load calculation. And then we continue to load to lift. So, what is load to lift? Load to lift is the preliminary crane load without dynamic loads or skew factor. So it's pure only the object's weight, which in this case is a gross weight. And then we have rigging weight and hook and ribbing weight. This load we use as a reference during lifting operation, so we can compare the actual load shown in the crane's monitor and our estimated load. This will be very helpful if we are performing multi-cranes lifting, especially for 3 or more cranes involved. During operation, the banksman will refer to our load to lift when doing the job. He will use our load to lift to balance each crane's load from 0% until 100% of estimated load. And it will help them to justify if any crane need to be adjusted. So that's for the load to lift. And the formula is gross weight plus rigging plus hook and ribbing. Next one is about the gross weight. Gross weight is the weight of the load that already consider contingencies and uncertainties of COG. One of reference that we can use to estimate the gross weight is Dian OSH205 in the section 6.2.1.1. It is mentioned the weight of your lifted item is often based on calculation only. In such cases, weight contingency factor 1.1 minimum should be used to define the design weight. So yeah, we can use that 1.1 based on the TNP. Otherwise, we need to have a look another reference that's saying different, or for an option, maybe you can refer to ISO. To simulate the uncertainty of COG, there are two commonly methods that can be used. First is COG envelope, and this generally used for lifting in operation involving 3 or more cranes. And the second is COG factor. So here is a example to calculate gross weight. Let's say we have a platform size 20 by 10 meters. The COG location shown in the picture here. Total weight is about 1,000 kilonewtons, and we're gonna lift it by utilize 4 cranes, which are located as shown in the picture. Crane 1, 2, 3, and 4. What is the maximum gross weight of each crane if we using a COG envelope and COG factor? First, we will check with the COG envelope, right? To check the COG envelopes, we will put the original COG at the center of a box, which is the size. In this case, I will refer to GNV OSH205, section C200. I have highlighted here. It is mentioned the size of the envelope is not less than 0.05 from its length, 0.05 from the width, and 0.05 from the height. But in this case, we only use the length and the width since we are not going to check the stability of the object. So now we have the size of the box. 0.05 from its length. The length is 20 meters, so 0.05 from times 20 is 1 meter. And 0.05 from its width is half meters here. And then we put the box at location where the original COG will be at the center. So it will be half of the length, So 1 meters, half meters to the COG1 and 4, and half meters to the COG2 and 3. And then we put another COGs. This is a imaginary COG at the corner of the box. So we have COG1, COG2, COG3, COG4 at the corner of the box. So these COGs will represent the critical COG position that possibly happens if the objects are tilted or any imposed load from specific crane during operation. So now we have a five potentially COG that we should check. First is the original COG, the second is COG1, the third is COG2, COG3, and COG4. After that, we continue to get the crane's reaction based on each COG's location. Remember, we now have 5 cases that should be checked here. The net weight here is the crane. Net weight here is the crane reaction due to the original COG. And then the case 1 is the reaction due to COG1. Case 2, reaction due to the COG2, and so on. Once we have finished with the crane's reaction for all cases, we call as a crane's net load. And then we compare all the net load from each cases, and we use the maximum load from each cases. So this is the maximum. This maximum is taken from comparison from the net weight case 1, case 2, 3, and 4. So we use the maximum load from a particular crane to check its capacity. For example, from crane 1, the maximum load is 223.13 kilonewtons. Then it is our reference to check capacity of crane 1 by getting the gross load first. And then we need to apply the weight contingency factor, which already mentioned before. It's a 1.1. So we multiply all the net load with a 1.1, and then we get the gross weight. So that's the gross weight calculation by using COG and fluff. So yeah. Now, how about the COG factor? It is simply just applying a factor to the net load. In this case, I refer to the NVOS H102, which is saying that COG factor 1.05 is normally to be taken. So in this table, it is shown the net weight. That is the crane's reaction based on the original COG. And then we multiply with weight factor and COG factor 1.05. For example, for crane 1, the net weight is 200 kilonewtons, and then we multiply with 1.1 and 1.05. Then we got the 231 kilonewton for the gross weight. That's for gross weight calculation. We continue with to the hook and reeving weight, or sometimes this reeving called as a part line. This weight must be calculated based on the actual condition of its crane. What is the actual hook type? What is the actual boom length? How many part line attached to the hook? What is the working radius, and how high is the boom tip? All these things will impact to the hook and reeving weight. So for the hook weight, we can find it from the catalog or manual book, and to calculate the ripping or part line, we can use this formula where n times q times h, where n is a number of part lines installed, q is the width of a single part line per meter length, and h is maximum length of part line that measure from the boom tip to the hook. So yeah, for example, I took from LR 11350 crane here. This table I've got from the manual book. So let's say we have a 1,350 tons hook capacity attached currently to the crane, and the rope diameter is 38 millimeters. And this crane is going to be used to lift a structure with a rigging height 36.71 meter. Lift point distance to the bottom of the tracks is 2.58 meters. 2.58 is pretty small, yeah. 2.58 meters plus 5 meters here. So the total will be 7.58 meters. And then with the radius 30 meters, this is 30 meters, and boom length 78 meters. This is the boom length. We've got boom tip height is 76 0.61 meters. Then yeah, 76.61 meters. Then the part line length is the part line length is a boom tip height minus the total of rigging height and lift point distance to the track. So we've got 32.3 meters, the distance from the hook to the boom tip. Once we got the part line length, we now can calculate the total weight of the part line by using the formula previously we have mentioned, n times q times h, where n is part line numbers. There is 32 numbers because we have 32 part line attached to the hook, and q is 5.9 kilograms per meter. That is the mass of single part line. You can find this information from the manual, and usually it is based on the diameter of the rope. And then the h is the length of the part line. We already calculated. We got 32.3 meters. So the total mass is about 6,098.24 kilograms, or equals to 6.1 ton. Then from the catalog, for the hook weight, we got 40 tons. That's for 1,350 tons hook capacity. So yeah, we got the 40 tons here. It's actually it's a range between 30 to 40, but we take the maximum one because sometimes the part is not if some parts cannot be we can choose either it's installed or not. So let's say all the parts of the hook already installed to the hook, so it will be the maximum weight, 40 tons. So the total hook and reeving now is hook plus reeving, part line plus hook is 46.1 ton here. So that's for the hook and reeving calculation. Any question from your side before we continue this?
Any question? So Nelson, we have our class today and tomorrow. Okay, so 2 hours and 2 hours.
Okay,
Just
okay,
wanna
no problem.
remind. So everybody, do you have any question regarding this calculation?
This calculation, no, but the previous table, if possible, the table of the COGs. I do have just one question.
This,
Could you go to the previous,
yeah,
please, Nelson? Previous table of the COG, not this one. After this.
after this. Yep.
So, for the case 1, 2, 3, 4, could you please just repeat how did you get these results?
So
We
the
have a
case
network.
one, yeah. So this net weight is we calculate the crane. It's a crane reaction calculate based on the original COG. So by using the COG envelope, now we have 5 cases that should be investigated, right? First is a original COG, which is at the middle of the envelope itself here. And then the second case is the COG one here. COG, and then we have a COG 2, 3, and 4. We should investigate all these cases. So this net weight are the crane reaction based on the original COG. And then the case 1 is based on the COG1. Case 2 is based on the COG3, 2, and then and so on. So first we need to find so we need to know how to calculate the crane reaction based on the COG. So actually, it's not in this class to explain this, but I will explain it how to calculate that. But this only works for a rigid structure. If it's not rigid or there is a flexibility on the structure, we need to consider the material elasticity to get the crane reaction. So let's assume that this is a rigid structure, yeah. We will try with the CO origin the net weight. So it will be based the crane reaction based on the original COG. First, we will distribute this COG to one pair of sides. You can choose either it's to the left or right or to the top or bottom. But for this case, I will choose that will to be distributed first to the left or right. So it will be crane 1 and 4 and crane 2, 3. So it will be distributed to the crane 1, 4 and crane 2, 3. If we look at to the side, then we can simplify the system become like this. This is the COG setting, which is 1000 kilonewton. And then this is crane 1 plus 4. And then this is the crane 2 plus 3. And the dimension will be 12 meters and then here is 8 meters. So now we just simplify it by using a undeterminate static structure. Now you can calculate the crane 1 and 4 reaction and crane 2 plus 3 reaction. Once you got the crane 1 and 4 reaction and crane 2, 3, this, for example, the crane 1, 4, the load will be distributed first to the at this point, right? And then now we can distribute to the each cranes, crane 1 and 4, and crane 3 and 2. Also same with the undeterminate static calculation by seeing to this direction, then we can use simplify, become like this. Now this is no longer the COG, but it's a reaction of the crane 2 plus 4, and then this point is crane 1. No, it's crane 1 plus 4. Sorry, crane 1 here, crane 4 here, and the distance will be 5 meters. 5 meters. So you can use the indeterminate static calculation to solve this to find the crane's the crane's reaction, but that's only for we just calculate for one cases, and then once we complete the case 1, which is the original COG, which is based on the original COG, and then we continue with the COG 1. Now we move the COG to be here, and then we recalculate with the same process as the previous to get the crane's reaction based on the COG if the COG is here. And then once we complete that, then we continue for the COG 2, 3, and 4. That's how I get this reaction. All right. And
Perfect,
then
perfect. Thank you.
yeah. So you got yes it.
Yes, I got the idea. I got the idea.
All right.
Okay, thank you. Thank
Yeah,
you, Nelson.
perfect.
Thank you.
Thank you.
Carry on. Thank you.
Anything else?
Any other question from Aldo maybe or from Rajesh? Do you have any question? Or Freddy? Do you have?
No, this is no, this calculation about for the gross weight is so the calculation is only about for the load, so it's not about for the COG of the crane. So this is my reminder to everyone. No, the calculation for this is talking only about the load. It's not about the crane. It's how much is crane will lifting in each point. Now we have 4 points, so it's clear how he explained, Nelson.
Yes, correct.
So it's only for clarify, because maybe there is some confusion with our college. So just it's only a reminder that this calculation is only to see how lifting each crane in each lifting point. So that's it.
Yes, correct. So the first thing we need to clarify that this only for the first one is we will talking about the crane stability based on the load. That's why we we put the example by only talking about the how to the crane load, how to get the crane load if we have four cranes arrangement on the structure like that. So we haven't talked about the crane's stability based on the COG yet, but we will. That's all. Is there any question?
Rajesh,
If
do you have any question?
Nothing.
Nothing? Still okay, yeah?
still okay. All right, we continue. So yeah, that's for the hook and reefing calculation. We continue to the rigging weight. So for example, I think you have familiar with the rigging weight calculation. So for example, we have a technical building here going to be lifted from the vessel to the yard. And this is the rigging design at the table. Now we are going to calculate the rigging weight. Since the COG of the structure is at the center of between the lift points, then the rigging design are same for each point. So here I will calculate the rigging weight for one lift point, and then I multiply it with 4. So that's the total rigging weight. But if you have a different rigging design for each lift points, then you need to calculate the rigging weight for another lifting point. So for the shackle weight, you can refer to the catalog. For example, here we have a 200 tons green pin shackle P6036. Then we look for its weight in the green pins catalog. So for 200 tons, the weight of the shackle is 235 kilograms, or equal to 0.235 tons. So, and for the sling weight, you also can refer to catalogs. It depends on sling diameters and what is the material. Either it's a polyester or a wire sling. The polyester sling usually has a lighter weight than the wire sling. Usually the weight shown in the catalog is per one length unit. So then you can suit the weight based on the length of you have in your design. So in this case, we have a 90 millimeter diameter for with 16 meters length over here, and it will be same with the 90 millimeter diameter with 16 meters length. We got 0.587 tons for the weight, and then we total them together. We got 1.5194 ton rigging for weight for one lift point. And then we multiply it with 4 because we have 4 lift points with the same rigging. Then we got 6.0776 tons for the total rigging weight. That's for the rigging weight calculation. Now we continue with the dynamic factor. Dynamic factor is factors that we should apply into our analysis that will represent dynamic load during lifting. As I have mentioned before, the dynamic loads can be caused by environment condition like wind, wave, and other things that possibly can move the object horizontally or vertically. And then cranes movement, and not limited to the elasticity of the crane's boom also. can causing the dynamic impact to the object. The dynamic factor we can refer to GNV H2O5 here. Table 3-1. If you want to do lifting onshore, like a fabrication yard and construction sites, for example, in condition the crane is not moving, you can use the first column in the table here. But if you want to do lifting on the water, you can choose dynamic factor in table 2 and 3. Now, what is the difference between inshore and offshore? Inshore is a location that already designed to be protected from high wave, like a port or harbor, while offshore is not protected at all. So that's why the dynamic factor in offshore, if we look at to the table, that's why the dynamic factor in offshore is bigger than in inshore. Now, what if we are going to do lifting onshore, but the cranes are moving? As we see in the table notes number 3 here, it is mentioned we can refer to section 6.2.3.2. And if we open the section, it is saying that we can use dynamic factor inshore in table 2 if the cranes are moving like that. Now we continue to the skew factor. Here we will refer to GNV and
sorry, Nelson.
Yes.
Before to pass the next slide, please can you explain when onshore, offshore, inshore, please?
This
What is the mean?
onshore.
Yes, thank you.
Yeah. So if we want to do lifting on the land base, like in fabrication yard or construction sites, or like in construction sites, we can choose the dynamic factor onshore here, but with condition that the crane is not moving, so it's only slewing or rotating. For the lifting on the water, we have two options here. First is a dynamic factor inshore and dynamic factor offshore. Now, what is the difference inshore and offshore, right? Inshore is a location where it is protected. It is designed to be protected from the wave. For example, it is like a port location or harbor location. There is some structure protected to protect the wave to coming to the port, right? But offshore is the location that it's not protected at all. So the waves is pretty high at the offshore rather than the inshore. That's why if we look at the table for offshore, it is bigger than the dynamic factor for inshore. That's how to, so we need to choose either it is inshore or offshore. Now, the next question is, what if we do the lifting at the yard, but the crane is moving? Here there is an option. It is mentioned in the note number 3, C section 6.2.3.2 for recommendation to moving cranes onshore. So if we look at this note 3, we open this section, it will be mentioned that we can choose the dynamic factor inshore for a moving cranes onshore. So yeah, that's how to. And then don't forget to use the static hook load information also. So if we lift the object weight and the rigging weight combined, the weight is between 3 tons to 100 tons, then we can choose the this dynamic factor. And then 100 to 300 is here, 300 to 1000 here, 1000 to 2500 here, and more than 2500 is here. The bigger static hook load, it will have a smaller dynamic factor. So yeah, that's how to choose a dynamic factor we are going to use. Is that clear, Aldo?
Yes, Nelson, it's clear.
Yeah, perfect.
I don't
Thank
know,
you.
my other colleagues is clear or no?
Other participant, because it's common, yeah, sometimes so we confuse when we have to use onshore, inshore, and offshore, especially inshore and offshore. So we have to clear understand what is the difference between onshore, inshore, and offshore. So
Yeah.
before you calculate engineering stuff for your lifting study or lifting engineering, you have to clear when you have to use onshore, inshore, and offshore for your calculation. So Yasid, do you have any question for this, or do you have any experience
No.
calculate this before?
Yes,
My only experience is the onshore. Only.
Onshore. So do you?
Yes, but I understand. But I understand that inshore and offshore depends on the protection from the wind. For example, inshore you have some I don't know, some construction, something that prevent the wind from attend to the load 100%. But in offshore you have 30, 60 degree, the wind can attend to the load. Can Hello? Hello?
Yeah.
Sorry, bad signal now.
So you understand, but in your area do you have onshore, inshore, and offshore operation?
We do have onshore operations.
Onshore, yeah.
Inshore and offshore, no, because I work in the desert. Desert is
Okay.
onshore.
Okay. Yeah. So thank you so much, Yasid. How about
Welcome.
Rajesh? Do you have any question, Rajesh, about this? Or Freddy, do you have any question?
Okay. Sometime no, it's every time. So we need to attach the draft or dynamic factor. We need to attach always the offshore when probably in the future, no, probably in Algeria. Somebody's working in Algeria here? Yes?
Yes.
Yes,
So in
yes.
Algeria, so right now it's starting one project over there, okay, oil and gas. So there, of course, is coming a lot of equipment for offloading from the sea because and also it's coming a lot of from ponton. We will put the one crane on top the jetty, and we will lifting from the ponton or from the barge to put on top the jetty, not the platform onshore. So in this operation, don't forget that we need to attach the offshore dynamic factor. It's not means offshore is only on the sea, full sea. No, it's sometimes we put the one crane on top the jetty and the load is on the barge. Okay, so if the crane is working in the onshore, so we need to work with dynamic offshore. You got my point? Somebody understand?
Yeah, so you want to say that you will use the dynamic offshore when you are doing the lifting in Algeria, when doing the installation, right?
Yes. So now in Algeria is to everywhere. So right now
Everywhere,
it's
yeah, yeah,
coming,
yeah,
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 yes,
yeah,
in
yeah.
everywhere.
Correct, correct.
No? So
Yeah,
this is
doing.
just as example, no? So don't forget to we need to attach this factor because
Yeah,
it's
yeah, yeah,
very important to understand because sometimes this is the reason that some trainings collapse
yeah.
because
Correct, correct.
don't have we didn't see how is the wave, no, or the
Yeah,
wave, the or the tide of the
yeah,
sea. So this is
yeah.
important when we need to attach the offshore dynamic factor.
Correct, correct. Yes, yes, yes.
The tide is very important. So okay, this
Yeah,
is a part of that we need to include also in this to clarify.
yeah, correct. But if you uh sometimes the we could calculate the, that's why I mentioned as before that we will not go into detail about the dynamic load, because there is another way to calculate the dynamic load in lifting operation. So we can calculate it based on the height of the wave and the how the response from the structure or the base from the barge to the crane movement. We can calculate them manually, and the result will be less than the dynamic factor offshore shown in the as per the DNV. But the problem is it's very long to calculate the only the dynamic factor. That's why it's better to simplify it just using the dynamic factor, and then it will be very safe, because it's more than the if we calculate it manually. But sometimes when we facing the problem that when we use the dynamic factor as per DNV, it's very high, and we are over limit the crane capacity. Now, if we're facing that problem, then we can choose to use the to calculate it manually. But when it's still okay with the dynamic factor, then we are okay to go with this factor. That's all. Is there
Yes.
anything? Yeah. Yeah.
Now for me it's clear. So when we need to attach each factor in offshore, onshore, and inshore. So just my question is only for reminder, no?
Yes,
So
yes. Correct.
sometimes we saw many accidents with
Mhm.
screen collapse, and
Yeah.
I hear also because somebody say no, the mistake is because the load is
Mhm.
not according to the drawing. The load is high. It's not the high.
Mhm.
The problem is the crane when working from the jetty to the barge for offloading any equipment, they don't attach the offshore dynamic.
Correct. Correct.
The problem is not the load. The problem is the crane not have enough capacity.
Yeah.
This, this is many mistakes there are, but right now, so we are improving this.
Yeah. The problem is not on the load. The problem is on the crane capacity. Correct. I agree
Yeah,
with that.
correct.
Yeah. Yeah.
Thank you.
Yeah. Is there anything else before we continue?
Any question? If not, we can continue to the next slide.
So far, so good.
So far, so good. Thank you,
All
Yasin
right.
and Aldo. So we can continue for the next slide.
Okay, we continue. Now we are going to the skew factor. Here we will refer to the DNV, and it is mentioned if we use two hook lifts in our lifting, we can apply 1.05 skew factor. Or if the lifting involves more than two cranes in here, you can use 1.1 skew factor. So these skew factors are applied to represent the unbalanced load distribution by the crane. That could be happen if the actual crane's load during operation is not same as what we have designed. And then the load differences will give impact to the other frames. So it could be higher or lower. So always remember to include this Q factor if you are working with a multi-crane operation. Now, once we have calculated all the loads from gross weight of the object, rigging weight, and then the hook and reeving weight, now we can calculate what is the utilization capacity of this crane. This utilization check is to decide if our crane capable or not to do this job by comparing the load and the capacity in percentage. For what is the maximum UC for the crane, you can refer to the project or your company requirement. Like in my company here, we are only allowed to use the cranes if the UC maximum is 80%. And I believe it refers to the ASME maybe. Now, how to calculate the UC? Basically, it's just a load per capacity times 100%, but the load here should be load to lift with dynamic factor, and skew factor if you have multi-cranes arrangement here. And the load to lift is gross weight of the object plus rigging and hook and reeving. So if we are limited with the UC maximum 80%, then if you find your UC is 90%, that means you cannot use the crane, or you can use, but some additional requirement need to be fulfilled. Whatever it is, just refer to your project or company regulation. So yeah. Is there any question until this for the UC calculation?
No, just you can provide one example how
Yeah,
you
yeah,
calculate,
sure.
and we will interpret how
Correct. Yeah.
when
Yep.
we will attach any factors.
Yeah. So
Okay, dynamic and skew.
yep. So now we are continue with the study case. Yeah. We are going to do lifting for a technical building, which is 1000 kilonewton weight by utilize lever LR 11350. Boom configuration SL, that means main boom only. And then the boom length is 78 meters. And then the radius is 29 meters. So we are going to find out what is the CUC for this crane. First, we will calculate the gross weight of the technical building. Gross weight is net weight times weight factor, which is 1.1 times COG factor, which is 1.05, then 1000 times 1.1 times 1.05, we get 1155 kilonewton. And then we continue by calculating the rigging weight as per we have calculated the mass before, right? Here. And for the mass, we get the 6.0776 ton. And then to get the weight, then the weight mass times gravity, which is 9.81. Then we got the rigging weight is 59.8 kilonewton. Now we calculate the hook and rigging weight. Hook mass is 40 tons, as we are using 1,350 tons hook capacity here, same as the previous arrangement. Then the mass hook is weight times gravity, and we got 392.4 kilonewton here. And then we calculate the rigging. Since I don't have AutoCAD here, so I will use this crane chart to estimate the part line length. First, we set the chart according to our crane's requirement. Boom length is 78 meters. 78 meters is here. And the radius is 29 meter. 29 meter is approximately here. So by assuming the minimum distance from boom tip to hook is 6 meter. 6 meter. For this you can refer to the manual book. Then we can calculate the boom tip height for 78 meters, boom length, and 29 meter radius is about 78 meter from ground level. So it will be, let's assume that this boom will be rotated to this for the 78 meters 78 meters boom length. Then the boom will be like this. Sorry. And the hook will be here, correct? So the boom tip is here, the black color here. And this is a 6 meter distance between the hook to the boom tip. Okay. So we can assume that the boom tip will be sitting during the 29 meters radius. The boom tip will be stop at 78 meters height here. 78. Now and then we have a rigging, correct? We have a rigging plus structure height is 32 meters. That the rigging plus structure is 32 meters. This is the 32 meters here. So the and then we have rigging okay 32. Then the part line length is now is 78. This 78. The part line yeah. So when the rigging is here, then this hook will be going down here, correct? The hook will be here. So the part line length will be 78 minus 32. And so we get about 46 meter here. That's the part line length. And then the total mass of the part line is numbers of the part line, which is 32 times mass times mass for the single part line times part line length Then we got the total mass of the part line is of 8,684.8 kilogram, or equals to 8.7 tons. So the N is 32 numbers. The mass of one single part line is of 5.9 here, Q, and the H is 46 meters here. So we get the total mass of part line is about 8.7 ton. And to get the weight, then we need to multiply with the gravity, which is 9.81. So we get the weight of the part line is about 85.3 kilonewtons. Then we total them together, hook plus reeving, then we get the 477.7 kilonewton. So yeah, that's for the hook and reeving. And then we continue to the dynamic factor that we are going to apply. Since this operation is onshore and the crane is not moving, just slewing, then we can use the dynamic factor onshore. That mention is here. Now the total weight, the total static hook load is the object weight plus the rigging, which is more than 100 tons, but less than 300 tons. Then we can choose the 1.05 dynamic factor here. And then because it's a single crane, then we no need to use the skew factor, right? And then we calculate the load to lift, which is a gross weight plus rigging weight and hook and reeving weight. Then we get 1,692.5 kilonewton for the load to lift. And then we check the crane capacity in the crane table, but unfortunately there is no capacity for radius 29 meters. So we will use interpolation to get the capacity. For radius 28 meters, we got 213 tons capacity here. And for the radius 30 meters, we get the 194 tons capacity. And by interpolation, we get the 203.5 tons for capacity for 28 meter radius. And then we continue with the calculation of utilization. It's a load to lift times dynamic factor times skew factors divided by crane capacity times 100%. So, but we don't have a skew factor here, so we can take it out from the calculation. And then we get the UC is about 89% of the capacity. So now it depends on your regulation if it's a go or no go to lift it with 89% UC. For me, here it's not it's a no go for the lifting operation. So we need to rearrange, maybe changing the radius, or if possible we put the super lift counterweight like that. So yeah, that's for the utilization check for this crane. Is there any question for this?
Thank you, Nelson. So far, so good.
How about yeah.
Yes, one question. When you say that we have capacity 203, okay, 0.5, from where is coming?
Sorry?
When you say the crane have capacity 203, okay,
The crane
so you
capacity?
are, yes, the capacity, because this is, or probably is the line is that you are interpolate 213 with
Yeah, correct.
194,
Yep.
but no is 194 with 178, because if now is less. You get my point?
During the so yeah, we using interpolation to get the 29 meter radius, right?
Yeah.
Yeah. And then for the load, yeah.
So we need to summary is 213 plus 194.
Yep.
Yeah, but yeah, because it's probably in your mark is there is some mistake.
What is that?
Yeah, because you are interpolate 30 with 32, and this is 28 with 30 meter radius.
28. Well, it's supposedly 28 with 30, right? And
with 30, yes.
And 203.5 tons is between 194 and 230.
Yes. But the
Right?
mark is yes, it's okay. Yeah, but the mark is there is some mistake. Okay, so in this
213.
yeah,
Yeah.
in our presentation that we received, if different.
All right.
Maybe when we try to make bigger and then the position for the marking is
Yes.
yeah,
Yes,
because
so just
Nelson prepared.
it's only
Okay.
clarify, because
Yeah, maybe sometimes when I try to make a bigger table, so it's more clear, and then the interpolation marking is yeah.
Well spotted. Well spotted, Aldo. Thank you,
Yeah,
Aldo.
thank you, Aldo. Good. Yeah, we have to be careful, yeah, because you know what, this is sometimes I just like drag the table, no, make bigger, so it's more easy to see, and I didn't notice that the marking is moving also. Yeah, so thank you so much, Aldo, for this.
So yeah, I think that's the end of the
for today, right? So tomorrow we will continue again. So for today, do you have any question regarding this? Because tomorrow we will continue for the new topic, and then new complexity, right? For tomorrow. Tomorrow we will start to calculate for the ground bearing pressure like this. So for today, do you have any question?
Yes, I have.
First of all, sorry, Freddy. Go ahead, Freddy.
Oh, okay. Sir, I just want to ask about the interpolation.
Yeah.
So far, as I know, we don't use interpolation in make a lifting plan, because when we have a condition like this, when the radius is not in the load chart, we use the smallest one. Like this, we have 28 meters with 230 ton, and radius 30 meter we have 194 ton. We use the 194 tons as I know. We don't use the interpolation because some manufacturer in the lot chart say that we have to use the smallest one.
Yeah, sometimes the manufacturer also mention it in the manual. If you have the radius that that didn't mention in the low chart, you can refers to the lowest capacity. But for this crane, the sliver, we can check if you the software like Lycan software from Liber. They sometimes if we do we, so if we put the 29 meters radius with the same configuration as we calculated here, it will be showing the interpolated capacity. So yeah, again, you need to read your manual book before you started the lifting plan. Correct. I agree with you.
Okay, thank you.
Yeah, how about you, Yasid? Do you have any question before?
First of all, thank you, Nelson. It was really, really beneficial. Thank you also, Dian. Thank you, everyone. Just for before we go to more complex calculations regarding the ground bearing pressure,
Yeah.
I know that COG will play a huge role in the calculation of the ground bearing pressure, and I know it's not in the training. But if
Yeah.
possible, tomorrow, just do small summary for COG calculations, just if possible.
All right. I will make a simple calculation for that, so everybody can understand. We are in the same boat to go through the next calculation. So yeah, I will make a simple calculation for that.
I appreciate it. Thank you so much.
Sure, no problem.
Thank you, Nelson. Good
Thank
job.
you, Aldo.
Thank you,
Thank
Dian.
you.
Thank you, everybody.
So much. So, and any question from Chris or from Rajesh? You unmute. Maybe you have any question.
Nothing, ma'am. We will study and let me know tomorrow.
So far you understand, yeah, for our topic for today.
Hello, Dian.
Chris, do you have any question?
Yeah, sorry for me. I'm not in the. I'm
Yeah.
not full in the session according to my occupation. Just for me, tomorrow, if you can send to me a summary of calculation of the COG, calculation of COG of the load of the loading and the crane.
Oh, okay. I will send you for also for the recording, yeah. So you can
Okay.
listen again for our topic today.
Okay.
Tomorrow we'll continue with ground bearing pressure calculation, and hopefully you can join full time, right?
Okay. Okay. Thank you.
Thank you so much. So, do you have any question, everyone?
Dian.
Yes, Tarek.
For me, all is clear, but I think that we've spent a lot of time on the basics.
Mm-hmm.
The last of each one of us has more than 10 years of experience in lifting engineer.
Mm-hmm.
For tomorrow, I hope we'll be able to concentrate on the COG calculation, like what says Yazid or Rajesh.
Okay.
No, it's not a COG. We are not concentrate with the COG calculation tomorrow. We will be focused on the ground bearing pressure, while the COG calculation is the complement just a simple just to showing the simple calculation to make it better to make it you got the
it's on the base of the COG calculation that we want to kind of calculate the ground bearing pressure.
Yeah, correct.
So tomorrow we will continue with ground bearing pressure, but you know, like some crane they provide for software, right? But you have to understand what information that you have to type into your software, so you will get correct information from your software. If you type the wrong information, so you will get wrong result from your software. So sometimes people say that, is it easy to calculate ground bearing pressure because we get the software from the crane? Not all crane provide you for the software, because if you get if you have a crane with old age, so they don't have software to calculate your ground bearing pressure. Or if you have ground bearing pressure software but you don't understand what information you type into your software, or you type wrong information, so of course the result will be wrong. So it is very important for all of us understand the basic calculation, the manual calculation, and then Nelson tried to explain about how important center of gravity for our lifting operation, because lifting operation, if we said about safe lifting operation, is all about center of gravity, is all about load distribution, is all about force and load weight calculation. So it consists of lifting equipment calculation, how we calculate center of gravity for the load that we lift, right? And then the second is basic rigging calculation. Basic rigging, we talk about lifting gear we use for the lifting operation. And the last is mobile crane stability. So we talk about equipment that we use. So there is 3 components we have to understand very well. And all of this involve for the center of gravity. You have to understand how to calculate center of gravity, load distribution for load you lift, and then and also the lifting gear that you have to use. Either you have to use the spreader bar to ensure that load distribution equal, or you don't need to use the spreader bar for your lifting operation. And then center of gravity for your crane, and also ground bearing pressure. So if you understand 3 of the component, we believe that you will more expert, and you will be more qualified for the safe lifting operation. And at the end, when you want to level up your career, become management level, you have to understand lifting management system. This is like a comprehensive system for all of this, like this. So lifting management system will be the top of your knowledge if you want to go up with management level, like this. So like APLO, SME, or project managers. So you have to understand about lifting management system, so you can analyze where is the lack of your operation. And we know very well crane accident mostly come from routine lift. We know very well of this, right? So be careful when you have a routine lift, like simple lift. Be careful, because when you start to lack of your awareness, so there is probability, big chance for you to create accident. I think that like Nelson, you involved for the heavy lifting operation, you involved for the topside lifting operation. Now also you involved for the SPMT operation, right? Even though you're not fully in charge for the SPMT lifting operation, I believe also Aldo, Rajesh, Chris, Tarek, and Yazid, and also Freddy, we know very well that routine lift, simple lift is create more accident in our industry. So routine lift or heavy lift involved for the lifting operation. After that, we can talk about skidding, jack, roller for the lifting operation, how we combine all of that. So we know that sometimes the crane cannot reach the load, and then we start to think about innovation to combine between jack up or roller or skidding to reach the load. So this is more complex, right, Nelson? I know that you involve all of this, Nelson, with McDermott or your previous company, or even with your company now. So maybe, but this will be our advance. You have to understand the basic first, and after that you can go up with the advance. So we can talk specific like lifting operation plan for combination using crane and jack up, or we can combine between crane and then the other type of lifting operation to support your operation. This is from me. So do you have any question, or Nelson, do you wanna share some of your experience in Azerbaijan?
No, I'm clear.
You okay? So thank you so much, everyone. I will share I will share our recording, and I apologize for the wrong marking. Thank you, Aldo, to raise up this concern so everybody understand this. Yeah, because sometimes Nelson sent it to me slide presentation, and I saw that this is too small, and it's just to drag, and then the marking move. This is a lesson in learning. So thank you so much, Aldo, to raise this concern. So if you don't have any question anymore, thank you so much for today. I will stop recording.